So again, good afternoon, everyone, and welcome to the second technical workshop under this series. And this one is entitled Introduction to Object Detection with YOLO V8. So thank you for attending our session for today. This was supposed to be last week, but we moved it due to the typhoon. I will give you a very brief overview of the workshop for today, the abstract, and also some prerequisite knowledge that you have to know before you attend this workshop. No, so the workshop will provide you a brief introduction to object detection and the YOLO family, leading to the development of YOLO V8. You as attendees will also learn how to set up, train, and evaluate YOLO V8 from scratch. Additionally, we will also cover technique for tuning the model to optimize its performance for various applications. So as part or the outline of the workshop, first part, you will have like a brief introduction to object detection and YOLO V8. The second part would focus on setting up the environment for training the models. Next would be loading of a pre-trained model and some demonstration. The next part would train YOLO V8 from scratch, including some hyperparameter tuning. And lastly, you will also learn how to evaluate the model. So some prerequisite knowledge, you are expected to know the following topics. You should have like a basic understanding of machine learning, including what are hyperparameters, knowledge of neural networks like weights, loss function, and backpropagation. That's a prerequisite, and also a basic idea of what convolutional neural networks are. Um, Towards the end of the presentation, we are going to provide you with the copy of the notebook or the Jupyter notebook that we are going to use for today. And we are also going to give you a recording of this video and the assignment file, no, that we always give to our participants in the workshop. So in the invite that we sent you, we have already listed down the dependencies and installation links that you can use to run the notebook. Okay, so for this afternoon, let me introduce our speaker. Our speaker for today is Juan Carlo Azarcon. Carlo is an undergraduate student at Salle University. He's pursuing a degree in computer science as part of the honors program or the BSMSCS program. Currently, his research focuses on object detection, which is our topic for today. Object detection of aphids. Aphid is like a kind of insect, that we're trying to detect so that we can filter out mga pests in our crops. So Carlo is focused on integrating a component or a filtering component in the detection process so that we can enhance the performance of object detectors. So without any further ado, I will give the floor to Carlo.
So hello, I am Carlo Azarcon, and welcome to my workshop, the Introduction to Object Detection using YOLO V8. So before I go over the notebook for this workshop, I'll briefly show slides just to have a brief introduction on the topic. So welcome again to Introduction to Object Detection using YOLO V8. So I'll define it first. What is object detection? It is a computer vision task that aims to localize and classify objects. So this is different with your usual classification task seen below, where it is just basically predicting the class of an object in the image. The difference here with object detection is that it is a combination of both classification and localization, where first it locates the object of interest in the image. So here we can see that locates the cat first and enclose it in a bounding box and then proceeds to classify it later on. Now for the things to remember, first is bounding boxes. which is a rectangular border that defines the location of an object in an image. The example here shows a format that uses 2 points on opposite corners, which are x1, y1, x2, y2, where you can already enclose the object in a box. Next is intersection over union, where it is a metric that quantifies the overlap between two bounding boxes. So in getting your evaluation metrics, you usually compare the ground truth and predicted box. So your IOU is just your area of overlap divided by the area over union, which is the combination of the area of the two bounding boxes. So here are just examples of bounding boxes where the prediction becomes higher. The prediction becomes better as the IOU becomes higher. So the red box gets closer to the green as it produces higher scores, with the excellent being almost overlapping with each other, the red box and the green box. Now, in your evaluation, you usually set an IOU threshold to filter out those poor detection, which is applicable to this metric called the mean average precision metric, which is an evaluation metric to assess the performance of a model in object detection tasks. So there are two known standard metrics for this, which is the Pascal-Vogt and the COCO, which represents their MAP in different ways. So for Pascal-Vogt, it is the average score of all classes using IOU of 0.5. Meanwhile, for COCO, it is the average score of all classes using IOU equals to the range 0.5 to 0.95 with an interval of 0.05. So this is just good to keep in mind, especially when comparing your model to existing models, since you would want a fair comparison between the models. So just keep that in mind whenever you are performing benchmarking and evaluations. Next, since we're going to use YOLOv8 as the main model for this workshop, I'll just briefly introduce the history or the different version of You Only Look Once or the YOLO models. So the first model is the YOLOv1, which is one of the first single-stage detector, where it combines the localization and classification task in one stage, as opposed to the two-stage detectors, such as faster RCNN, which has multiple stages for those tasks. Next is YOLOv2 or YOLO 9000, which basically introduces the anchor boxes, where they are predefined boxes generated by the model as the starting point for its training. Next is YOLOv3, which performs multi-scale predictions, where it captures objects for different sizes. Then next is YOLOv4, which introduces the concept of bag of freebies and bag of specials, where the bag of freebies pertain to modules or new modules and data augmentation strategies that could help in training, while bag of specials pertain to modules and post-processing techniques that would help slightly improve the performance of the model. Next is YOLOv5, which is the first model by Ultralytics, which is the library that we will use for this workshop, where they introduced auto hyperparameter tuning and augmentation within its model. Next is YOLOv6, which removes the anchor-based detection of from YOLOv9000 and introduced an anchor-free detection head. Then last is YOLOv7, which provides a modified version that extends a modified version of YOLO, which extends the architecture, producing better detection performance and while maintaining the speed of the previous models. Now, this leads to Ultralytics YOLO V8. Actually, this is not the latest model as of now. The latest model of YOLO is YOLO V11. So this is one of the latest. I think it was created last year, 2023. So here are basically the contributions of YOLO V8. So YOLO V8 has an improved backbone and neck architecture for better feature extraction. Next, it borrows the idea of anchor-free detection, where from YOLO V6, where it applies that to its detection head. Then next is the balance between speed and accuracy. And lastly is the simplified training and deployment through their Ultralytics library. Now here is just the YOLO V8 architecture, where I will provide a brief explanation and I guess a general that's applicable for most object detection architecture anyways. So the backbone here does the feature extraction for hierarchical features, given that there's multiple layers. The higher the layer, the more high level the features are extracted. So this includes the entire object detection, while the lower layers look into more the finer details such as the edges and the shape. So that's where it's extracted there. Next is the FPN, or also known as the neck, where it processes and combines the multi-level features from the backbone, and then this is fed to the detection head, which can help with detection. So the detection head is where you get the outputs of the bounding boxes, the class scores, and the object next scores. Basically, the bounding box is their coordinates. The class scores is similar to the in classification task, where it has a higher score of it shows the score of the highest class it predicts to, and then the objectness score, which basically just shows how much the detection is detected as an object. So that is all for the brief introduction of the topic. I'll go over the notebook now. So for the notebook outline, first we will be setting up the dependencies and libraries. So first is having Python with a version of greater than or equal to 3.8. So I think they changed it actually. I think the minimum version for Python for PyTorch is to have a Python version of 3.9. So just keep that in mind. Next is PyTorch, which I provided a link where you can choose. It serves as a guide where how to install PyTorch, where you can choose your version for CUDA and CPU, and then just follow this guide and you can install PyTorch in your device. Next is CUDA, where it's dependent on the GPU that you have, but here in this website it contains all the versions that CUDA has released. So just keep that. Just find your version that's applicable to your device and download it there. Then to check if your device is CUDA compatible, I've also provided a link where you just have to search for your device here and then check which versions of CUDA is compatible for that. Next is the Ultralytics library, which we will be using for this demo. So for the Ultralytics library, the link here also provides you a detailed explanation on how to install it in your device. I would suggest actually creating a virtual environment for this, since it may conflict with different versions of your dependencies for other stuff. So just keep that in mind as well. Now, there's another alternative for installing Ultralytics as well. And this is useful for if you want to modify your the model, or if you want to do a custom training loop, if you want to modify their training loops, since we will be using the default functions of Ultralytics. If you want to modify their training loops or their functions, you can just pull their repository and clone it there, and it will do the same thing as installing the library. So here's how to import the library. This will show if you have your CUDA available and it's installed properly. So it should state that it's true. Then next is the demo of the pre-trained models. So for the pre-trained models, Ultralytics actually provides a lot of pre-trained models that you can access here, can easily define. So for YOLO V8, here are the list of pre-trained models that you can use. For the detection, I think it's pre-trained on the COCO dataset. So you just have to look into those. Now to load the model, you would just have to do YOLO and then the model equals YOLO V8N or whatever version of YOLO V8 you would want, and then .pt. The first time you would run this, it will download the weights to your directory. So yeah, this is how to load it. Next is performing as a demo. I'll perform a demo on sample predictions for this model, for the pre-trained model. So here's a visualization of the sample image that we will be detecting. Now, to perform a prediction, you would do model.predict. You would call .predict, where you would feed an array of images or array of the image location or the path location of the images, and then run this. It will produce a results object, which is a list of objects that is pertaining to an image. So let me show this. So to get the detections of the first image, you would want to access the first index of the results object. So results and then index 0. And then to get the detection itself, you would want to get it through dot boxes, which contains all the detections for that image. And then to get the individual coordinates for each detection in that image, you would want to do dot xy or any other format that they have supported in the library. There's also XY for width and height, and a normalized version of XY and XWH. And then for the class, the predicted class, you would want to get it. You would get it from box.cls, and then just map it through the dot names, which contains the indices of the class. So here is the example of the detection. So it has 3 detections: the bottle here, and then a chair here. Now, Ultralytics actually automatically generates already bounding boxes or visualizations. If you would want to access them, you would just have to go to the directory in which the prediction is saved. So predict.demo, predict demo, and then sample1 shows the image here. So it shows the class as well, the bounding box, and then the specific confidence score for that object. Now, next is loading a dataset. So Ultralytics actually provides a lot of datasets for detection benchmarking. So you can just access it through that. Now, to call it or to download them, you would just during training you would just do data equals and then the name of the dataset and then .yaml, which will automatically download the dataset from the web. Then next is what if you want a custom data set for your own project? So I'll show you the folder structure for a custom data set. So this is the African wildlife data set. So this is the African wildlife data set, and here is the folder structure for the custom data set for YOLO. With the main directory, inside the main directory, you would have the data.yaml file, and then the folders for the corresponding sets. So the test set, train set, and validation set. And then inside the folder, or inside the set folders, you would have the images and labels. Inside the images, you would have the .jpegs, or the image files itself. And then for the labels, you would have the annotations itself corresponding to the images. So for the label files, here's how they annotated, or YOLO, here's how YOLO annotates their labels or their objects. So it is in a form of normalized XY WH. So the first value here is pertaining to the class index. So I believe 0 pertains to buffalo in the animal wildlife data, African wildlife data set. So this is the class index for buffalo. And then the next 4 is the bounding box coordinates, with the first 2 is the x1 and then y1. And then the next 2 is the WH, or the width and height. So this is the normalized version. Usually labels can be in the form of pixel values as well. So to convert that into the normalized version, you would just divide it by the dimensions of the images. So for example, for x and the width, you would divide it by the dimension of the width dimension of the original image. And then for y and h, you would divide it by height. The next is the YAML file, which you will be feeding to, which will serve as input for your model. So the YAML file contains first the names of the class and their corresponding class index. So you just list it down here. And then for the number of classes, you also list it down, as well as the path of the main directory. And then the path of the images per set. So train set, train images, vals, validation set, val images, and test set for test images. Actually, the test set here is optional, since the Ultralytics library doesn't actually require you to have a test set when calling their functions. So this is optional, but you can just include it for your evaluations. Next is actually if you want, before I go to the YOLOv8 from scratch, if you would want to perform your custom training loop, you can actually, another approach that you can do is do the traditional data loaders from PyTorch. So you can just define your usual data loaders from PyTorch. The difference between your classification data sets from the object detection data sets, the labels in object detection contains the bounding boxes and the class corresponding to the for each detection. So it's a list instead of just one class compared to classification task. Next is YOLOv8 model from scratch. So it's still similar in loading a model from scratch. Still similar with loading from pre-trained weights. The difference is you use .yaml file. You use .yaml file instead of .pt. So this will load a model without any trained weights from scratch. And then to train the model, you would just have to actually just call .train with the parameters here, which I will go discuss. So first is data, which pertains to the data set that you would want. So this points to your data.yaml file or .yaml file. So in this case, from the African wildlife dataset, it's from dataset, African wildlife, and then the data.yaml file. So this would read the custom dataset that I have implemented. Next is val, which just indicates whether you want to perform validation for every epoch. So after epoch, you would perform a validation for the current epoch. For every epoch, you would perform validation or evaluation with the validation set. Set in your data set. Next is cache equals true. Basically, this is just for memory utilization to speed up your training process. So just add caching here. Next is the device usage. This is pertaining to your GPU. So if you have multiple GPUs, you would want to specify the index of that GPU. If you would want to use multiple GPUs, you can indicate a tuple. So to be just like this, and it will use multiple GPUs. Then for Apple chips, Ultralytics actually supports Apple chips, so you just use MPS for training. Next is the hyperparameters, which first is the number of epochs, so basically your training epochs, and then the batch size, where it also has a training mode if you specify a percentage. I mean an auto mode if you specify a decimal. So for example, if you place 0.7 here, it will automatically set the batch size to a number that would utilize 70% of your GPU usage. So that's one convenient thing with this library. Next is your optimizers. So I believe Ultralytics has the Adam optimizer and SGD optimizer. It also has an auto option where it chooses, it performs the hyperparameter tuning for you. So you don't have to manually specify your learning rate, your optimizer, and your momentum, and so on. So the auto option is convenient for faster training, and you don't have to manually set your hyperparameters. Yeah. Now for LR0, this is your initial learning rate. So the learning rate to begin with, and then LRF is your final learning rate factor. So the final learning rate is your LR0 or your initial learning rate times the learning rate LRF. So at the end, it will be 0.0001 if I calculated that correctly. And then next is your momentum factor, which is 0.9 or by default, which you can specify there. Next is sample augmentations that Ultralytics provides. These are just sample that I have included, but we still have more in their website list. So first is image size, where this is basically just the resolution and dimension of your image. You can also do a tuple for this if you would want to modify the width and height of your image. Basically, if you just place one value, it will just get the highest. It will just resize the highest dimension from the original image. Yeah, and then resize it there. Next is translate. This basically moves the image a fraction of the image size. So this is helpful for training your model with images that are partially unseen, with the objects partially unseen. So maybe the object is slightly to the right or to the left. That's only like a portion of the object is seen. So if you would want to train your model with that, you can include translate. Next is scaling, which just increases the object size. So with a higher scale, the objects may appear larger. for the model. And then for smaller scales, it will appear further from the model. Next is Mosaic, which combines four training images into one. So these two are actually useful for um, the robustness of your model itself, with mix-up blending two images and their labels. So this will add difficulty factors whenever you're training with your data. Next is just your saving parameters for your directory. So saving here is equal to true to save to a directory, and then save period is the checkpoint saves for every epoch. For every epoch, which checkpoint do you want to save? So right now it's currently set to 1. So every epoch it will save the weights for that. Next is seed, which just reproduces the results, so just a randomizer. Next is the directory of the project and the name of the folder that you would want to save it in. So to save time, I actually ran this before since it took a while to run. I ran it with 5 epochs. Ran the training with 5 epochs, and this is what it looks like whenever you're training. It will show your GPU memory usage, box loss, class loss, and your focal loss. So these are what you want to keep in mind whenever you're training to make sure your model is actually training well. And then automatically with the .train function of Ultralytics, it actually performs validation testing at the end of your training session. So it uses the validation set by default. So if you want to see results immediately, you can just refer to this. Next is if you want to do custom training and testing loop, I have included it here. This is in correlation to the data loader that I have mentioned a while ago and how to implement them. So for custom training loops, you would want to get the PyTorch models itself. So with dot model, you would get the PyTorch models, and dot train, you are able to do the usual training and testing loop with the PyTorch models. So since Ultralytics actually uses PyTorch models for its implementation, you can actually access them through dot model. Then next is in the case where your model's training is interrupted or you paused it, you can actually resume it through loading the model from the last saved weight. So you can do it with last.pt, and then model.train with the parameter resume equals true, which automatically gets the previous setting that you have set for your training, and then as well as the configurations for the gradients and the loss functions, and so on. So it's just a convenient function to use whenever you're training and it gets interrupted. Next is evaluation. So to load the best model from training, best model pertains to the highest performing based on the list of models the list of checkpoints that you have saved. So best pertains to the highest highest performing among those checkpoints. So this is how you load them again. And then to perform evaluation, you will do model.val with the data YAML again, the YAML file as your dataset directory. And then for split, since by default it uses the validation set, if you have a test set present, you can actually just define it here with test. And then next is the batch size. And then the confidence, which pertain to the confidence, IOU, and max detection. These are actually post-processing threshold, which can further improve your detections. So these basically filter out your detections after the model list out the detections it has. So for confidence, this pertains to the scores of your the scores that your model gave to the detection. So how confident the model is that the object that it is detecting is an object and belonging to the class that it detected it into. So this is a threshold that you can set here. So the higher the threshold, the more strict it is. So the more higher the values that you want to keep. Next is IOU. This pertains, instead of pertaining to MAP IOU, it actually pertains to the NMS IOU, which basically helps in reducing the duplicate detections. So the IOU threshold here is basically a threshold where um, at 60% IOU, whenever there are two detections intersecting with IOU of 0.6, it will automatically drop that detection. So the lower the IOU threshold here is for the NMS, the stricter it is. So the more duplicate detections are dropped, basically. The next is I'll actually run this since it might take a while. Next is maximum detections, which just pertains to the number of detections that you can have in an image. So basically just limiting in case that there are too much detection and it might take a while for detecting. So let's just wait for this to finish. This should produce the metrics, the MEP metrics for IOU 50 and 50 to 95. Hold on. I wait. Think I will. Uh, I guess I'll discuss the next few. So if you'd want to if you do not want to use the default the built-in evaluation of ultralytics, you can actually perform extraction of predictions through the dot predict again, similar to it's not. I think it's connected. And here are the results for the MAP for each class and as well as the class in total. So since this is just 5 epochs, it won't produce that great of a score, or nonetheless, these are the results for it. Now you can get the prediction metrics or the evaluation metrics if you want to get it manually, or the individual values for it. You can actually access it through the model or the object that this function produces. So with metrics.box, you can get the MEP score for MEP 50 to 95, MEP 50 and MEP 75, and then MEP 50 to 95 per class, which is a list. Now, the Ultralytics actually also produces a visualization. So if you'd want a confusion matrix or visualize a confusion matrix, you can just access it through the different images that it generated. So here is the confusion matrix that it provides. As you can see that it didn't really produce great results since it's just 5 epochs. Or here's the example. So going back to extracting predictions. Now, if you don't want to use, or if you want to use your own your own code for calculating your own metrics for MAP, you could actually do dot predict to get the bounding boxes, similar to what we did with the pre-trained models or the demonstration in the pre-trained models. So here in dot predict, instead of inputting a list of images, you can just do source equals the path of your test images. So the test images are located here. And then similar to the dot eval, you can also specify the different post-processing thresholds that you can apply to the detections. So I'll demonstrate the difference or the effect of the thresholds. So for score thresholds, I will set it to 0.001. And then for NMS or IOU, I'll set it to 0.6, which is the default. So let's just wait for this to load to perform a prediction. With these values, we expect this detection to have a lot of duplicates, and then a lot of bounding boxes, unnecessary bounding boxes in the images. So we would see this when it loads. If there are any questions, you can also place them in the chat while we're waiting for this to finish. How long does it take to predict an image? It depends on the image size, where usually it's quite fast, but it also depends on your device as well. Usually for larger images, of course, it will take longer. Or on average, it shouldn't take that much for a single image itself. So this is done. This is what it looks like with the confidence threshold of 0.001, IOU of 0.6 for NMS. So visualization. As you can see, there are a lot of unnecessary detections and duplicates. So if we set the confidence to a stricter value like 0.1, hopefully this doesn't take as long. And okay. And then compare the visualization from there. Actually, reduces it for quite a lot already. So the bounding boxes here, or the detections here that are left, are actually those with confidence scores of higher or equal to 0.1. Now, since there are multiple detections or duplicate detections pa, we can actually further filter this with lowering the NMS or the IOU to 0.5, or it just removes whenever there are overlapping bounding boxes. So here is the resulting bounding box prediction. Now, similar to the demo for the pre-trained, you can also find a generated visualization from Ultralytics. So here is the sample visualization. For choosing the confidence and IOU, it's situational, I guess, for depending on the type of detection you're doing. So for example, in my case, I do pest detection. So usually pests have there are a lot of objects in a single image for pests, and usually they're overlapping. So if I would want to set an NMS threshold, I would set it to remove duplicate detections, but also keep in mind that it doesn't remove the overlapping detections for different objects or different pests. So I can answer questions. I'll briefly go over the practice activity first. So I also provided a practice activity. Basically, this contains the different steps that we did from the demo notebook. Also has brief descriptions on or guides on what to do. So you can just follow this. And then for just a demonstration of a real-time detection use of the YOLO models, actually prepared code for for Ultralytics.predict, which uses the webcam as a real-time detection, or applying a model to the webcam. So I'll just turn off my video just to demonstrate this. There. So it performs real-time detection using the pre-trained weights that I uploaded a while ago. So let's see, detects, well, it's not that good at detecting, but yeah, it performs the real-time detection with the model. I think that's all for the notebook. I'll just answer questions that we have in chat. So for bounding boxes, so hi, for the bounding boxes that have an IOU score larger than the limit, would the outputted bounding box be the one with the highest confidence level? Or is it the first generated bounding box that has priority? Actually, when you visualize them, you would usually get all the bounding box with the IOU score that's higher. So all of the bounding box with the will be included in the visualization. To reduce that, that's where the NMS comes in, where you would want to set an IOU threshold as well, where you would reduce the duplicate detections. Yeah, you would reduce the duplicate detections for that. Next is, can I also use the YOLO pre-trained weights for medical image segmentation? There are, in the website, I believe there are, I'm not sure if there's, actually there is, for segmentation, there's pre-trained weights for segmentation. However, I don't think it's directly applicable to medical image segmentation. So I think you'd still have to train the segmentation model from scratch. Yeah. Uh, I think those are all the questions for now.
Thank you, Carlo. Any other questions? I actually have a few questions myself while we're waiting for more questions. Now, upon listening to the presentation, there seems to be some parts of it, since we have already mentioned to the or in the invite that the students or the participants should be knowledgeable in some of the topics. No? But just for the sake of the students attending without any idea about some of these topics, can we like can you discuss more about the idea of confidence in terms of
S-
action?
so given your model, you feed them, for example, a sample image. So the images contain the objects, of course. So the model does the prediction there. Now, every prediction of the model or every detection of the model has a corresponding value, attached to it, alongside the bounding box and the class. And the confidence value pertains to the model's confidence on how it detects the object as the specific class and as an object itself. So basically,
Okay.
so the higher the value is, the more confident the model is that it is an object.
Okay. Can we see like the visualization of that one again in the first few parts of
Okay.
the notebook?
Uh, Here is the example of, so here.
Ayan. Yeah.
So this is the Ultralytics visualization. It shows your class, bounding box, and then the value here is actually your confidence score. So it's 0.33. That's the confidence score of your model for predicting that that specific object is a bottle.
Okay. I'm actually asking on behalf of some of our students attending now, because some of our students, this is actually like the first meeting with our next batch of students under the research center. So since they are only doing CS model now, I think they are doing CS model or they did CS model last term, and they do not have like ST-INSI yet or the machine learning class. They would have a lot of questions about certain ideas that were discussed now. Um, so it was mentioned before that this numbers pertains to the confidence, or if I may explain it in Tagalog, ganito yung model mo, ganito ka confident, no, in saying that this specific object is a bottle. This specific object is a bottle and this specific object is a chair. So that's our concept of what we mean by confidence. And in the last part of the presentation of the notebook, it was mentioned by Carlo as well that this confidence um, can help us in trying to filter out those detections that are of low quality. When we say low quality, that means the detection or the confidence for that detection is too low, that the model is not even sure of the detection, or the confidence is too low for us to say that it's a confident detection. Tama? So that's the idea of confidence, and you'll see that again. That's the idea of confidence is used in object detection and also in classification models. Now, there are some like questions that I have prepared here when I was listening to the presentation. Can you like give an idea to the listeners? What do we mean by pre-trained models?
Basically, these are models that were previously trained already. So you're just basically loading them. So in this case, in this example, these are the model that I have loaded here is YOLOv8n. That's pre-trained. That's pre-trained to the COCO dataset already. So it was previously trained by other authors and just loaded here.
Okay,
So it's like a plug and play model already.
right. So I just want to add more on top of that, no? We're using pre-training or the idea of pre-training because um, if we want to use a model and it's already been pre-trained, meaning train na siya for a specific other data set, it's actually useful at least according to years of research that you use a model that is already pre-trained on something else. The idea is when you're training it for a new data set or if you're going to use it for a different data set, but it has been pre-trained on an existing data set already, some of the objects existing in the previous data set used to pre-train the model can actually be used as, or the features that you have extracted there are actually useful as well in your new data set. No? So there are like, let's say, there are objects in the previous data set na are similar to the data set that you're trying to train your model on. So the idea of pre-training helps because features, these visual features that we see across different images are actually universal. So that the idea of how a bottle looks like from one data set to another data set is the same. So we can use like a model that is already pre-trained in a comprehensive data set like yung nabanggit ni Carlo, like Coco. It's a comprehensive data set, so we can use the features extracted from that to be able to apply it as well for our special data set or the data set that we're working on. Now, there is also a question earlier about like the how fast prediction is, and you mentioned something about input image size. So can you emphasize on that? Like, what are the usual input sizes to an object detector?
Usually it's what do you mean, sir, by input sizes?
What is the usual input size to an object
The
detector?
usual input size. Usually there's no standard where it's I usually use is 512. It's usually to the power of 2, I think.
Yeah.
Yeah, it's the power of 2. So
Oh,
around those values, usually those are the usual values for your image sizes.
okay. Just to give further context, no, in the history of object detection in Pascal, VOC, and even in the MS COCO dataset, these are two popular datasets. The usual input size back then, since I think we're limited by the GPU as well, is 300 by 300. And that's a very small image size. So, ang popular dyan is 300 by 300 and 512 by 512. And we usually stop there for object detection task. For classification or input size, at least in the ImageNet dataset, is 224 by 224. Imagine those are very small dimensions. No, our phone cameras right now, our DSLR cameras are capable of taking like resolution higher than 2048 by 2048. But when you feed it to or you give it to object detectors like this or classifiers, it is usually rescaled down to 300 by 300. So imagine having like 4K resolution, but when you give it like to an object detector, it will be scaled down to 300 by 300 or 512 by 512. That's the usual input size. And it would take some time for it to pre-process. But I also like the part of the presentation earlier showing um, yung live video being wherein YOLO is predicting Carlo to be a person. No? So we're seeing that YOLO is working in real time for that specific use case. This is my last question. And this is just to add more context, no, and to help those that are unfamiliar with detection or in computer vision in general, or those who are starting out. Can you give like more insights on why do we perform augmentation? What's the idea behind augmentation?
First is, for example, you lack if there's a data set problem, if you lack the number of data set. Basically, if the number of data sets available from your resources is lacking, so data augmentation can help with that by performing cropping, duplication, or flipping of your images. So just to add variation to the images during training. Another is for measuring how robust your model can be. So for various situations, it can adapt. So for example, what I have mentioned are the augmentations of um, mosaic and mix-up. So those basically combines or blends multiple images into one. So which can be difficult for the model, um, originally for the model, pero with using that as a training image, it may help with future predictions for their performance.
Okay, that's good. An additional question. Are all of this the augmentations available in
There are actually more
more?
available for it. Yeah, I have a link below that you can use to
Okay.
follow it.
Okay, okay. So we'll just ask the participants to refer to that in terms of the augmentations. And just to add something into the discussion, we do augmentation because we assume that an object is still that object, even if you rotate it, even if you scale it, even if you change the color slightly. So the idea behind augmentations, um, imagine this phone, no? This phone, if you take a picture of it this way, it's a phone. But if you tilt it this way, it's still a phone, right? If you tilt it this way, it's still a cell phone, right? If you flip it over, it's still a cell phone. So we're trying to give more variations into the data set. So if your data set is only composed of cell phones that are upright in nature, something like this. So all of the pictures of the phones in your data set uh, are like this, and you want to introduce variations, you can do some augmentation to tilt the image, and it's still a cell phone, no? So we're trying to introduce imperfections in the data because real world data is imperfect anyway, no? So this is a pen. So if your data set is just composed of pens that are in upright position, you can try introducing some tilts, introducing some translation, or introducing flipping, um, introducing some changes in the color of the pen. That's fine because this, in its case, will still be a pen even if you change the color, even if you change like the rotation of the image. So we're trying to give more variations to the model so that it can respond well to changes in the data set. No? We're essentially expanding the data such that pag picture ng dog, if the dog I do not have like a picture here, but if you change like if you slightly change the orientation of the dog, it's still a dog. So your object detector should be able to recognize that, right? So I think there's a question here. Can you answer it, Carlo?
Okay, so what are good evaluation metrics to look at to assess the model's performance? Um, One of which is the MEP that I have mentioned here from a while ago. And then another, if you want to assess during training to see if your model is training well, is through the loss the loss values that it's printing out. So also, does it have a tendency to overfit and underfit? If so, how can we solve that? Um, Usually, overfitting and underfitting is one approach done is the mentioned data set augmentation, usually feeding the model with more complex data can help with the underfitting or underfitting and overfitting problem of that during training, as well as it's more of a general machine learning thing. It's just including dropouts or regularization on your model itself. It's modifying your architecture itself. So that could help as well.
Okay. In terms of the evaluation metric, it usually depends on the data set. So Pascal VOC has its own metric, but ultimately when we talk about object detection, it's mean average precision or average precision. Pero different data sets have their own interpretation kasi on what mean average precision is. So sometimes there is this concept of did you discuss yung what's this, the overlap, the IOU?
Yes, sir.
Covered that,
So,
right?
yeah.
So Pascal VOC uses an IOU of 0.5. Okay, but MS Coco, that's an entirely different data set, uses a different threshold.
Uses the
So
range.
yeah, yung range. But ultimately, they are using mean average precision. They only have like different thresholds. And the higher the threshold, the more strict the metric. Okay, I think that's a good question. Meron ka pa
There's
ba?
another question. How do we know if it's underfitting and overfitting based on the printed logs? Um, you can usually compare it with the validation. Usually it's paired with the validation. Uh, for example, for if it's overfitting with your training set, you would see that it um, performs well during training. So it has actually scores here during training. And now when you do it, when you perform evaluation with your validation set, actually performs a lot worse, even though it performed better. It performed great with your training set. So for underfitting, it's also a matter of plotting. I think depends on the plotting of your losses. And that's where you can learn if it's overfitting or underfitting. Uh, there also I skipped a few questions, pala. Will there be a performance variation if the device does not have a GPU? From what I know, it doesn't really have uh, a performance variation, assuming you have the same parameters and everything. It's just a matter of the the time it takes to finish the training and testing of the model. So it doesn't really have an effect, assuming you have the same parameters for all. And then next is, are there any ways to enhance confidence level? What I mean is, like, for example, there's my current approach is lowering the confidence threshold. To enhance the confidence level, it's for the prediction of your model, it's more of I guess making your model more complex or just training a few more epochs for it. Since the confidence threshold is just like a post-processing technique that you would apply after the detections have been done already. I think hopefully that answers the question. Next is, are there further demonstrations, links, or on modifying YOLOv8's architecture? Such as, actually, there are no direct links for modifying that directly. But since YOLOv8 actually uses, or Ultralytics in general, uses PyTorch implementations, you can follow PyTorch um, articles, links, or guides that refer to modifying or editing or implementing your PyTorch models for object detection. Uh, in terms of locating where it is in the Ultralytics, I believe it's somewhere here. It's one of the, yeah, you can access them here. Uh, next question. I think those are all the questions. I think this is just a curious. Can this YOLOv8 detect HTML elements, e.g. button? I think if you train, yeah, depending on what the data set, yeah,
Yeah. If you have the data, yes.
yeah, it's depending on the data set and annotations for it.
So earlier there is like a question about how do you improve the confidence score of the model? I
Yes.
guess there are multiple approaches to that.
Yeah.
One approach is you can improve on the model, or the other approach is you can improve on the data. So in training a model, sometimes the solution can be changes in the data set, or trying to make the data set more comprehensive or more representative of what you're trying to achieve. So sometimes the adjustments that you need to do really is in the data set. So if you have a good data set, then most probably, hopefully, you will have good results as well. Are there any more questions?
I think those are all the questions I've received.
Okay, sige. Thank you, Carlo. Thank you everyone for attending. Before we end, as usual, I would like to have a picture with everyone.
I'll share the link rin po for
Yes,
the
and
folder.
Carlo will also share the
Uh,
link to the
if you want the copy of
code.
the notebooks.
Yeah.